In the previous section, we have introduced the linear Diophantine equation of the form ax plus by equals c, where a, b, c are all integers. And based on the Basel identity, we have developed the criteria for the existence of integer solutions of such an equation. That is, ax plus by equals c has integer solutions x and y if and only if the greatest common divisor of a and b divides c. In this section, we will assume that this condition holds. That is, we're given the existence of integer solutions of a linear Diophantine equation. Now, we are interested in investigating the uniqueness, or rather the multiplicity of integer solutions for this equation. More precisely speaking, we would like to ask, if the solution exists, how many solutions there are? And in case of multiple solutions, how can we find all of them? These questions can be answered by the following proposition, which is the main result of this section. It claims that let ax plus by equals c be a linear Diophantine equation where the greatest common divisor of a and b does not vanish. In other words, a and b are not both 0. We also assume that a pair of integer solutions, namely x0 and y0, is already given. From there, an arbitrary pair of integers x bar and y bar also solve the same equation if and only if we can find some integer t, so that x bar is equal to x0 minus b over GCD AB multiplying t, y bar is equal to y0 plus a over GCD AB multiplying c. Notice that we are talking an if and only if condition, which means that if x bar and y bar is a pair of solutions, then we must be able to write them in a given form. On the other hand, if they can be written in this form, then they must be a pair of solutions. Also notice that if a and b are both equal to 0, then the left-hand side is always equal to 0, regardless of our choice for x and y. In other words, we will fall into a degenerate case where the equation has infinitely many solutions if c is equal to 0, or it has no solution at all if c is not equal to 0. This trivial case is somehow not very interesting, and that is why we have imposed the assumption that GCD AB does not vanish. Alright, now to prove this proposition, let us proceed with the sufficiency first. To this end, assume that x bar and y bar can be written in the desired form. We would like to show that they indeed solve the equation. Actually, direct computation shows that ax bar plus by bar is equal to a multiplying x0 minus b over GCD AB multiplying t plus b multiplying y0 plus a over GCD AB multiplying t. Now moving the factors a and b inside these brackets respectively and rearrange the resulted four terms, we obtain ax0 plus by0 minus ab over GCD AB multiplying t plus ab over GCD AB multiplying t. The last two terms cancel with each other, leaving us with ax0 plus by0, which is equal to c since we know x0 and y0 solve the equation. As a consequence, ax bar plus by bar is also equal to c, justifying that they form a pair of solution as well. This finishes the proof for the sufficiency. Next, let us study the necessity. To this end, assume that x bar, y bar, and x0, y0 form two pairs of solutions for the same equation. From there, we can rearrange the terms by putting everything related to a on one hand side and everything related to b on the other hand side. The equation thus becomes a multiplying x0 minus x bar is equal to b multiplying y bar minus y0. Since GCD AB is not equal to 0, we can divide GCD AB on both hand sides and the equation will still hold. To simplify our notations, let us denote by a prime and b prime the two quotients respectively. Also, we can assume without loss of generality that a prime is not equal to 0. Recalling an important property of greatest common divisor we have introduced in the previous section, we observe that a prime and b prime are co-prime to each other. This observation is essential. Actually, since a prime divides the right-hand side, and a prime and b prime are co-prime, according to the Euclid lemma, we conclude that a prime divides y bar minus y0. In other words, there exists some integer t such that y bar minus y0 is equal to a prime multiplying t. Plugging in this result back into the previous equation, we see that a prime times x0 minus x bar is equal to b prime times a prime t. Now, since a prime is not equal to 0, we can cancel the a prime on both hand sides, which in turn shows that x0 minus x bar is equal to b prime t. In other words, we have achieved the desired form of representation. This finishes the proof for the necessity. Now, let us summarize. Given the linear Diophantine equation ax plus by equals c, how can we study its solutions? First, we can compute GCD-AB using the Euclidean algorithm and check that GCD-AB divides C. This is a necessary and sufficient condition for the existence of solutions. If this condition does not hold, there will be no solution and our study stops there. Otherwise, if this condition holds, we know that this linear Diophantine equation will have actually infinitely many pairs of integer solutions. Now, reverting the Euclidean algorithm will provide us with a pair of integer solutions, namely x star and y star, satisfying the Bezout identity, that is, ax star plus by star is equal to GCD-AB. Since GCD-AB divides C, C can be written as m multiplying GCD-AB for some integer m. Now, multiplying m on both hand sides of the Bezout identity gives us a mx star plus b my star equals c. In other words, we have achieved a particular solution of the linear Diophantine equation. That is, x0 equals mx star and y0 equals to my star. Now that we know the value of a and value of b, to finish our mission, we simply compute the quotient of a divided by GCD-AB and b divided by GCD-AB. Putting them back into the formula of the previous proposition will give us the general solution with an integer parameter t. To illustrate these steps, let us look at an example, where we are asked to determine if the linear Diophantine equation 2024 times x plus 748 times y equals 132 has integer solutions. If yes, find all of them. As we have mentioned before, our first step should be the computation of the greatest common divisor of a and b, that is, the greatest common divisor of 2024 and 748. The Euclidean algorithm shows that their greatest common divisor is equal to 44, which indeed divides 132, as 132 is equal to 44 multiplying 3. Next, we want to find a particular solution of the linear Diophantine equation. To this end, we revert the Euclidean algorithm, which produces the Bezout identity 2024 times -7 plus 748 times 19 is equal to 44. Now let us multiply 3 to both hand sides, which in turn gives us a pair of integer solutions. x0 equals -21, y0 equals 57. Finally, dividing the coefficients 2024 and 748 by their greatest common divisors, we achieve the quotients 46 and 17 respectively. Plugging them back into the formula of our previous proposition, we see that the general solution is of the form x bar is equal to -21 minus 17 times t, y bar is equal to 57 plus 46 times t. Thus, we have successfully solved this linear Diophantine equation completely.